So how do we know if our model is a good model? All those other numbers, that's what they tell us. So again, this is what I was looking for before, minimizing squared errors. So we want to minimize the root mean squared error. When we're looking at as our model as a whole, this is what we want to minimize. So we use that squared, so our predicted hat versus actuals over our n value. You'll see that it's squared, so we'll make it positive. And then we find the square root. So one thing that a lot of machine learning and this model has, and they're similar, they use distance to evaluate models. So you'll notice that it, like, again, go back to probably geometry. This looks very similar to Euclidean distance, or what we would think of as the miles from here and the place that my home that I came from. So, but on this case, it's on a scatter plot, the distance value. So what this intuitively gives you is the distance between our predicted values and our actual values. So that's our root mean squared error. And we're finding that squared because then it gives us something that looks like distance there. And it's finding, and I'll show here, it's similar to the distance between the actual and the predicted values. And we divide by n, so it looks more like an average. So for a typical point in our data, or you can, on average, you can think of it as how big is our distance between our actuals and our predicted. That's what this means here intuitively. So that is used for linear regression, and that's the default for all machine learning models. If you have continuous variables, you can change it, but usually root mean squared error is used. Any questions? Yeah. So that's going to be the question is, do you usually normalize your data? So what surprised me is every time I've learned this, nobody had ever mentioned that to me, normalizing data. So since we're using distance here, basically when we get into using many predictors, if one predictor is really large and the other predictor is really small, the model is going to be biased by, and it'll show that the bigger range is more important, and that's a problem. So she asked about normalizing your data. One thing that will make it more accurate in a lot of cases is making those continuous variables, putting them all on the same scale. So either from 0 to 1, or coming back again to our z-scores that we talked about, you can change it into a z-score. Because if they're all within the same bounds, then they aren't going to bias the bigger values. That'll cover a lot more when we get into the AI side of things. It just blew me away that no one had ever mentioned that until I got into the machine learning space. So that's something, if you're going to actually use this model, look into that. If you use it before we get to that, but that is a problem. Anytime you use distance, that's important. So yes, the answer to that is yes. Any other questions? Okay. So this is the question that almost every time I go over anything like this, what is a good root mean squared error? There isn't a good answer for that. So there never is, because the units are your domain, what you're looking at is going to matter. So heart disease mortality is a pretty high number. You saw that it was in the hundreds, somewhere in the range, whereas a percent would be between 1 and 100. Just by default, if you were looking at heart disease mortality, it's going to be bigger than a percentage. It's just the way it is, the way we're looking at those units. So the units are going to matter here. So what you use this more for is when you're comparing multiple linear regression models, it's going to give you more information. So we will then go over that a little more later, looking at multiple models. Okay. So this is a really big deal. So we're going to go over R squared, just like the standard R squared first. We'll get to the adjusted one in a minute. So R squared is really important, and you'll hear it very, very often. So it's the proportion of variation in your response variable that is explained by your model. So if you are seeing an R squared of 70, that means that about 70 or 0.7 you would see. That means, and it goes from 0 to 1. So if you see 0.7, that would mean 70% of the variation in our response, so heart disease mortality, is explained by our predictor variables. So our entire model. That evaluates the model as a whole. The higher that is, the better it is. And again, there's no easy cutoff here. It's going to depend on looking for tissues, but I don't see any. It's going to depend on whatever units we have as well. If you're in public health, R squared, just because, or policy, is going to probably look pretty small because there are many variables going on. If it's something that you're looking at that has, I would say, for instance, if you're looking at our agriculture, and genetics are a very strong predictor of a lot of things in agriculture. So when you looked at a correlation of our predicted versus our actual values, it was usually around 0.7. So that's going to be higher in a domain like agriculture, where genetics really is a huge determiner of how it's going to do. You have a question?
So what do you mean by explained by the model?
Yeah, explained by the model. So that variation, so you can think of it kind of in the terms of our equation. So 70% would mean that one predictor variable is going to explain the variation or the change in that response variable. The other 30% would mean that there are extra things that we are not in our model, or additional things that explain the rest of that variation. So we're missing things in this case. So you can think of it as basically what we're getting, the variation that we're explaining, and that other percentage is, okay, you need to go out, for instance, and find more predictors that explain more of that error. I'm going to show this real quick because this might help. So intuitively, so in this case, we're looking at heart disease mortality and education. Clearly, education is only going to explain a small amount of heart disease mortality because there's so many other factors going on that would influence that. So you see exactly what I just said. Our R squared value is really small here. It's only explaining 5% of the variation in heart disease mortality. So our R squared values is small in this case. So we're not explaining much of heart disease mortality with education. So we'd have to go out, find more predictor variables that helped with that. So does that answer your question? Yeah. Yeah. So, and I'm gonna, So if you are thinking of it like mathematically, the third bullet is, so that would answer the question more in a mathematical sense. So this would be the square. So we're using square of the coefficient, the correlation coefficient, the correlation coefficient between our predicted and our actual values. So we find we get our predicted, our actual values, we find the correlation between those and square it, and that's R squared. Okay. Any other questions? Go ahead.
So when you put in the model, why did they call it multiple R squared?
So there are two, in this case, it's just going to be, so that would be multiple variables. That question was, why does it say multiple R squared? That actually isn't applicable here because we only have one predictor variable. But when we go into like models with more than one prediction, It's showing that it's multiple predictors. The adjusted R-squared is something a little different. We're going to get to that because it's not applicable here either because we only have one predictor. Adjusted R-squared is actually what we want to use for all our cases, but I can't explain it till we get to multiple regression. Okay. So now this is not an easy thing to explain. So this, try to picture, go back and look at the details. So our F-statistic at a very high level is our mean squares of our model. So we've seen this already. Our predicted minus our actual squared over our degrees of freedom, which is calculated with this. So basically what our model explains. So this is mean squared of model. So the sum of squares of our model is what we're looking at here. So the variation explained by our model over the mean squared error. So we, in this case, this is comparing it to the mean. So how much model does our model add, information does it add versus the mean? And then our denominator is going to be the error. So how much are we missing? And how much are we missing between our predicted and our actual values here? So think of it as a proportion, the variation explained by our model over the error in our model. So that's the F statistic, and that's how we see if our model as a whole is statistically significant. So, but if you can't understand this, because it's a lot of information, think of it as the variation explained by the model over the error. So obviously you would want the model to explain more than the error. And if there's more error than the model explains, it's not valuable and the p-value will be really high in that case. If we have a very high value here and a low value here, it's going to return return a p-value that is very low. So it will be statistically significant. Hold on one second. So to expound upon that, just 1 second. I'll come back to your question in just a minute. So we're assuming before we look at we calculate our F statistic is that all of the coefficients are equal to 0. In this case, it means there's no relationship. All of our coefficients are 0. The alternative hypothesis, and this is what our F statistic gives us, is at least one of our coefficients is not equal to 0. So it is statistically significant that it's different from 0. So that's the question it answers. And that's going to spit out a value. The bigger the better, because we want our model to explain more than our error. And then you go into something that, and I'm going to, it should have kept a link there. I guess it's not clickable, sadly. We go and edit hyperlink. So I apologize for that not working. So real quick, I asked somebody to put up here. So it's going to out a number. You're going to find that number in here. Look at our degrees of freedom, and then it's going to tell us what our p-value would be. So this is our cutoff, basically. But you'll have to go in through there and find it, but R is going to spit that out anyway. But if you want to go back and look at that table, it might help with how intuitive it is. So this is more relevant when there's more than one predictor. It's not really going to tell us a whole lot while we only have one predictor, because it is equivalent to a t-test when you only have one predictor. It's the same thing. So your question.
So in the previous slide, for the degrees DFE, you say n minus number of predictors. So what is n?
The question is for the DFE, what does n mean? N will always be our number of observations. Every time you ever see n in statistics, it means the number of observations in our data set. So I think it's around 3,100, whatever the counties is in our.
So essentially, in this case, it would be 3,100 minus.
Yeah.
Just removing that one.
Yes,
thing.
that
so
one
DFE
value.
Would be 1.
Yeah, so the question was, in this case, would it be, it's around 3,100 minus the number of predictors. We have one predictor, so that it would be, in that case with that example, it would be 3,099 in that case. And as I said, degrees of freedom is different for everything you look at, but it's always somehow related to sample size in some way. Like the parameters in our model and sample size, it will always be based on that in some way. So you just have to look that up, but it's always going to tell something about our sample size. And bigger is better in this case when we look at the F statistic. I'm going to go in real quick and show this example. So the F statistic is, by the way, residual standard error is the same thing as root mean squared error. What we just covered, they just call it something different in R. So if you see this, that means root mean squared error. And nobody calls it this, so I don't know why they do that. Everyone calls it root mean squared error, just makes it confusing. So our F statistic here, okay, so the actual number of observations in this case, is 3135 is going to be what it actually is in practice. I was rounding because I couldn't remember the exact number. So this is the number of observations. It's going to subtract 1. So that's telling us what our degrees of freedom is. And this is our F statistic that comes out of our model. So it is enough that our p-value is high. It's below that value. And it's just a cutoff. And that's something you have to look up because no one ever goes in and calculates the p-value from an F statistic. It's just, there is a distribution, and kind of when you see here, this is our F distribution, and each one of these values has a number, a p-value associated with it at a really high level. So that's what we're seeing with the F statistic. So are there any questions about that? That gives us our p-value here, associates with our p-value. We talked about that. All right, so which one do we use? R squared, root mean squared error, F statistic. They all have pros and cons, and we can never just look at one alone. You need to look at everything as a whole. And if, say, all of them are either high or statistically significant, then you're probably good to go. You're looking at a real relationship there. If, say, our p-value is 0.1 and 2 of the other parameters are really low, then okay, then we don't have a model that gives us enough information. So, and what's really frustrating about statistics, there's usually not cutoffs where one thing is, except for with p-value, that show whether it's important or not. It's just something where as you look at these things more and more and more, you start to get an idea of what's good and not. And then if you were actually using this as a prediction model, you would actually look at the predictions and see how accurate they were. And if they weren't accurate, it's not useful to you. So that we'll get to later. But so if all three agree, you're good to go. You're seeing something that's real, more than likely. Any questions? Yes.
I was trying to get my vocabulary straight. So evaluation methods, that's the same thing as validating a model? The question was, is evaluation and validating a model are the same? No. So validation is actually, we would put in a validation data set, and actually I'm going to table that because it's looking at the accuracy of our predictions. So the accuracy of the actual predicted values is validation. We're evaluating it by, say, looking at these values. Is this coefficient statistically significant? We're looking at our model parameters, basically. So all of this stuff is helping us evaluate the model. Validation we'll get to in one of the next classes very soon. But so is this model parameters almost the same thing as a performance metric?
Can you say?
Is model parameter, is that the same thing as performance metric?
The question was model parameters, is it the same thing as a performance metric? This is our performance metric. Root mean squared error is how that is considered a performance metric. So that's going to quantify how much error you have, is what you think of a performance metric as usually. So that's and there are several of them. Another one is mean absolute percentage error, which means something exactly what it's the mean absolute percent difference between our predicted and our actuals. So that's going to look at our actuals and our predicted every time as a performance metric. I guess our model evaluation is looking at everything. So our squared, a root mean squared error, our F-statistic, our coefficients, and how they're statistically significant. It's looking at the model as a whole, basically this output. Everything in here you would use to evaluate where or not. Good question. So another thing that's very frustrating about statistics, this is a great example. Everyone calls it root mean squared error, and someone might come up to you in a conversation and talk about residual standard error. And if you didn't know they were the same thing, you might be arguing with them over what it means, and it's actually the exact same thing. So a lot of times people call things like 5 different names in statistics, and it's really frustrating because you can think you're disagreeing about something, but you're actually talking about the exact same thing. So it comes with experience. It gets better. And Google.